Okay, everyone, sorry for the delay. So today we're going to continue talking about control systems. I have a quiz that's posted on Moodle. I posted it last week, but it's not due till the end of this week, or Sunday. So make sure you take the quiz. It's on the material that I hopefully should finish today. So the control system is when you have a controller that's controlling a plant. The plant is a term for any system you're trying to control, whether it's like a robotic arm or a motor or power electronics or some kind of physical system. The controller has inputs into the plant called manipulated variables, and the plant has signals that come back to the controller optionally called process variables. Now this feedback is something that you only get with a closed loop controller. So in open loop controllers, if you don't have any feedback, closed loop is when you have this feedback thing. Okay, so one way to model the plant and also to design and model the controller and then also model the whole system together is using an LTI system, a linear time invariant system. It's a differential equation that contains these signals. In this case, there's a U and Y are signals, so they're time series signal. And then you can also have, you can modify those variables, those signals by taking their derivative or integral, and then typically when you do that, you represent this, you take it from the time domain to the frequency domain, which actually makes it more convenient because everywhere you have a derivative, it's just S multiplied by the S domain signal value. So in this case, we have the derivative of y of t dt, and so that just becomes sys, capital YS. And then if you have the integral, then you're multiplying it by 1 over s. And if you have the second or third derivative or fourth derivative, you would then take s would be s squared, s to the third, s to the fourth. And likewise with the integral, if you have the second, third, fourth integral, then the exponent of s would be the corresponding negative value, right? So everyone comfortable with that? Okay, so the reason why we do this is because by using the S domain, the frequency domain version of these LTI systems, we can then calculate transfer functions and then feed one transfer function to the next by multiplying them in the as polynomials of S. So the transfer function is when you have when you calculate this as a output over an input, right? So what ends up happening here is you can see that in this differential equation, you have capital U of S and capital Y of S kind of all throughout the equation. The objective to be able to take this and put it into a transfer function form, you need to essentially have one side of the equation Y of S over U of S if you're calculating Y with respect, Y is the output and U is the input. And then on the right-hand side, you would just have typically a polynomial with S or a ratio of two polynomials with S, right? That's the goal. Does that make sense? So it's basically some algebra you have to do to get it into the transfer function form. So in this case, I factored out Y of S because I had Y of S multiplied against all three terms on the right-hand side, so I divided out Y of S and then divided both sides of the equation by Y of S to get one side with Y of S over U of S equals 1 over 1 plus S minus 6S to the negative first power, which is fine, except that typically there's an additional step here. Normally, the polynomial that you have would be would have its lowest term of be s to the 0th power, right? So you could take the numerator denominator here and multiply it by s, in which case you have s over s squared plus s minus 6, Make sense? Okay, so we talked about stability. LTI can be stable or unstable. What that means is whether the output, you want if the output is always finite for any finite input, then the system is stable. So in some cases, not in all cases, your objective with designing a controller is to make an unstable system stable by feeding it with a controller, right? Or putting it into a controller system, right? I mentioned there's a few different ways to determine if a system is stable. You can use the impulse response, which an impulse is just literally that. It's just an impulse. It's a value that's 0 everywhere except time equals 0, or it doesn't have to be time equals 0, but it's 0 everywhere except for one specific time. And the idea with that is that an impulse contains all frequencies. And the nice thing about the impulse response is if you have an LTI system or transfer function, and if you do the inverse Laplace transform on it, it gives you the impulse response in the time domain for free. So that's one nice thing with the impulse response. Another, you can do that, or in practice, I think it's more common to you can simulate an impulse response in MATLAB, right? So you can use a simulator. Simulators allow you to take an S-domain transfer function and put them in a block diagram with other S-domain transfer functions and connect them together, and then simulate it in the time domain. And so the impulse is in the S-domain this is 1, in the time domain it's that spike at time equals 0. And then another option is you can find the poles, which are the values of S that create a divide by 0 in the transfer function. Those are the poles. And if all the poles are in the left-hand plane, meaning that their real component is negative, then it's stable. If all the poles, right? You guys with me? So, if your denominator is a polynomial with a degree greater than 1, then you're going to have multiple poles, right? And S is a complex number, but in this lecture, I'm just focusing on S values that are real, just to make things simple. Okay, so those are the 3 ways that I know of to check stability. So I gave an example here where we did the reverse or inverse Laplace transform, and we looked at 2 different functions, 2 different transfer functions. This is an example of simulation. This is simulating in MATLAB. In this case, I'm simulating with the step function. This is a step function, not an impulse function, but it's similar to the impulse function because if the output is bounded in response to a step function, then the system is stable. In this case, it's not stable because, and I didn't plot very much time here, but you can see the trend here. This is the input, the step function, and the output is this kind of wave that is continuing to build up in an unbounded way. And just for the heck of it, I also put a sinusoid. Now, a sinusoid isn't necessarily going to make an unstable system blow up. It depends on the frequency of the sinusoid, but in this case, I put in a frequency that I knew would make it blow up. I gave it 2 radians per second, which just happens to match up to one of the poles. Yes?
So, I'm sorry. When you have this sinusoid/step function and you're trying to find if it's stable or unstable, do you need to change the frequency of the sinusoid, for example, to check whether it's unstable? Because my understanding that the unstable system is unstable at a specific frequency.
That's right, and that's what's happening here. So the reason people use step functions is in order to create a step function by adding sinusoids, you would have to add an infinite number of sinusoids in order to build a step function from sinusoids, right? Because obviously, if you look at a step function, this doesn't look like a sinusoid because it has these hard edges on it, right? So this step function can be realized by adding sinusoids together, and the more you add, the more it looks like a step function. But in order to get a perfect step function, where the slope here is infinite, from 0 to 1 on this rising edge, you would require an infinite number of sinusoids to make a perfect step function, and thus this input signal contains every frequency, right? That's the reason why and the same thing goes for the impulse, right? But that's not true for this sinusoid input I put in. So you're right, if I had changed this to be 3 radians per second, then the output would have been fine, would have been bounded. But because I put in 2 radian, I just used a 2 radian per second frequency, it caused that to blow up, right? And that's the reason I should have had another example where I put a different frequency in, but I didn't include that. Okay, does that answer your question? Okay. So here's an example of one that is stable. Okay, and then transfer functions. This is the part that I find to be pretty interesting. This notion that you can take transfer functions and treat them like blocks, almost like a block diagram in Verilog, almost. You can take these transfer functions and make them blocks, and then you can connect them together and build a system composed of multiple blocks. And you can connect them in any way you want. I mean, you can take outputs and add them together and have fan-ins and fan-outs, and you can do any arbitrary connection of these transfer functions. In this class, we're just going to look at very simple arrangements of these. But when you feed the output of one transfer function into the input of another, it's kind of cool. You just have to multiply. All you do is multiply the S-domain transfer functions together. You just multiply them. It's just algebra, which I think is, I don't know, I think that's pretty neat. But you guys probably seen something similar like this when you took your circuits class. But the one thing also I want to point out is this notation gets a little confusing. So normally when you have these block diagrams with transfer functions, they just have like one letter for the input and output signal. But that is actually a shorthand. This is actually like an input here of y of s, the output of g of s. And technically the transfer function is g of s over y of s. Although a lot of times you'll just see this as g, and the output will be g, and the input will be y. It's like a shorthand, right? So I tried to make this is actually kind of the full notation, but this is not normally how you see these things. You just usually have letters in there. Okay, so I also gave this really simple example, physics example of, the problem is you have a coin and you want to push it across the desk. You want to push it and develop a transfer function for that, the dynamics of that, pushing that. You could do something, I've seen a lot of examples too, like with springs, like applying a force on a spring. Those are all pretty simple physical dynamics problems, kind of the simplest type of dynamics problem you could have. In this case, I did this mostly just to show you an example of how you can conceptualize a physical system with a transfer function and then design a controller around it. So in this case, you have an input as a force, which is U. Now keep in mind that the inputs can be anything, depending on what you're modeling. Usually, if you're controlling a robotic arm or a voltage regulator or a motor, usually the input's going to be a pulse width modulated input value, right? So you guys have been doing labs with PWM signals. That's oftentimes what you'll see, because that's a natural way for a processor to send a input to a physical system. It's usually done through PWM. And that applies even, if you go out and buy a Tesla, the way all those motors are controlled are generally through, and all the voltage converters inside the Tesla are controlled through PWM signals. In this case, Y is not PWM. This is actually a force in newtons. And so the output is a position Y in meters, and then there's a mass and a coefficient of friction, which is B. So M and B are just parameters for the whatever system, whatever, the mass of the coin and the friction of whatever surface you have the coin on. And then the differential equation is U, which is the force, minus B y dot, and this is a new notation now. This y dot is just the derivative of y with respect to time. Likewise, y dot dot is the second derivative. And so in this case, when you have friction, the friction is applying a counterforce that is proportional to the speed that you're moving it. So the faster you push the coin, the more you're multiplying that by the friction coefficient of friction B. And then M times y dot dot is going to be mass times acceleration. So you've got the input force and then essentially your output force here. So this is what you're putting in and this is effectively what you're getting out, and then the only difference there is the friction that you have there. And the reason why I'm showing this is because it kind of shows how you can go from this down to a transfer equation. The way you do it is first you take this into S domain. So the y dot becomes capital Y, S capital Y. The y dot dot becomes S squared capital Y. And then you have to just basically you're moving things around. So ultimately what I want to get is y over u, because u is the force I'm putting in and y is the result, which is the position of the coin. And so y is the output. So what I want in a transfer function is y over u. So really all that's involved here is just rearranging these variables and doing algebra to get it into a form that's y over u. And eventually I get that here with, it turns out it's 1 over m divided by s times s plus b over m, right? Or actually I like this form better, 1 over m divided by s squared plus bs over m. So that's the transfer function. That's an unstable transfer function, and the reason is because if you give it an impulse, it kind of essentially, you're giving it, you're ramping up the force kind of instantaneously, and turns out it's not stable. Okay, so yeah, and that's the step response there. Now this actually makes sense though, because when you think about this, right, if I have 0 force and then I put 1 Newton of force in, but I just keep that force constant, obviously the position of the coin is just going to continue to go away. Yes?
It's just been a while since physics for me, but I thought the frictional force was calculated as the coefficient of friction times the normal force.
That could be right. I pulled this example out of a book, and this might be a simplification of it. But that's a good question. I'm gonna look into that. In this case, they're saying that the friction is proportional to the speed, the velocity. Okay, so that's just an example of a physical system model. Now, what I'm hoping to do in the next lab is, there's 2 ways to build models, by the way. One is to do it based on first principles. So this is an example of where I'm taking a system, I'm taking a physical system and I'm building it up just using first principles. Another way to do it is if you have a system and it's a black box, like you don't know how it works, but you can do some experiments, you can collect some data, some empirical data. Then you can feed that data into an algorithm, a system identification algorithm that'll take the data and will essentially curve fit a model to the data. It'll fit the model to the data, which is what we're going to do in the next lab. I'm going to take a motor and I'm going to fit data from the motor and build an S-domain model from that, so you have that model. Okay? And then once you have the model, then you can design the controller with that model, and then once you've designed it, then you can deploy it, you can implement it. Okay, and I don't know how the system identification stuff works internally. I've used it in MATLAB, but I've never actually built one. Okay, so then so closed loop control then is when you have a plant and a controller. The controller sends a manipulated variable into the plant as an input. These two things arranged this way is the open loop control. But then if you have a process variable that feeds back, okay, to the input, that becomes a closed loop feedback control. And in this case, the way this one's set up is I have a variable and I have a set point, which is my ref. And my objective is, one, I want to make the whole system stable. I want to make these two things together, or actually the whole thing, stable. But also, I want to be able to get this variable, which is, when I say variable, it's a time domain, time series variable, time series value, which is, the position relative to time, of like the position of the coin at a given time. I want to be able to, control that. I want to be able to have a set point and design a controller that will put the coin into a specific location, right? So the way you do that is you take that variable you want to control and you subtract it from your set point and then use the difference as an error term that comes in as an input to the controller, right? So this is the one way to do a closed loop control. Now, keep in mind that I want to emphasize that these systems are composable. So, like, if you drill down into any one of these boxes, these systems, this is like a hierarchical system. So, like, there could be another closed loop controller inside any one of these, right? But this just kind of represents one level of abstraction. Okay, so the closed loop control, I think this is the last thing I covered last time. So I mentioned that basically when you have a transfer function feeding into another transfer function, you just multiply them, right? Now in this case, it's a little bit more complicated because I have GC and GP, so those are multiplied together. But then I've got another term which is vref minus YCL. Okay, so I'm considering this thing YCL, this feedback connection. And I named it that because Y is the term I used to represent the position of that coin. So basically, again, this is essentially a robot that's moving a coin, right, is the idea. And so basically, what I'm trying to get is a transfer function that is in the form, I mean, this is fine. I mean, this is correct. But all you're doing here is trying to rearrange this equation to get it into a form of YCL, which is the position of the coin I'm trying to control, as an output relative to ref, which is my main input to the system. That's my set point for the coin. Okay, so essentially all this is just rearranging this to get into that form. But as it turns out, you can kind of generalize this. If you have an arrangement like this, where you have a controller, a plant, and your feedback, you can consider this part, these two, your open loop system, right? That's just your controller connecting directly into your plant. So that's just GC times GP, that's your open loop. And then the closed loop ends up being that over 1 plus that. Right, and that gives you your closed loop control, assuming that you're, using this, feeding in the difference between your controlled variable and your set point, right, as the input to the controller, right? Does it make sense? Okay, so one thing you guys probably already seen in robotics 274. Was this PID controller, proportional integral derivative controller. So this is a simple kind of controller where you take your objective here is to find, to fill in the controller value, right, the GC, right? So how do you do that? You take the error and you want to multiply the error by a proportional response and then send that into the plant, right? Make sense? So remember, the input is a force. The input to the plant is a force, right? The output is a position, right? So you're looking at a difference of position, and you're multiplying it by something to convert that into a force. So let's say I want to move the coin 1 meter, and I only have it currently at 0.9 meters. So the error there is going to be 0.1, and so that 0.1 then I'm going to use to figure out how much force to push the coin, right? So do I push it, 0.1 newtons? Does that make sense? I don't know, that might be overkill, right? Or it might not be enough. And that's why you have this KP term, which is the proportion, that's how much you multiply, that's the value you multiply against the error to determine what your output of the controller is, right? But then you also have the proportional term, which is another term that you use to multiply against the rate of change of the error, right? So basically, the faster the error changes, the more sort of the larger of a value you want to add in to the output. I mean, assuming your K value, K sub D, is positive. Of course, it can also be negative. You guys with me? Did you guys cover this in 274? Okay. And then there's also an integral value which works in a similar way, except in this case it's a third term that's multiplied against the integral. And so the idea with that is your error sort of accumulates, and the more you let your error accumulate, allows you to essentially correct for that, the accumulation of error, right? Make sense? Okay, now I don't know if you guys might have used a PID controller in robotics. You probably just used it kind of in the time domain. Obviously, this can be trivially converted into the S domain as well. So in the S domain, for instance, it's basically if E sub t is your error value, and this is in the time domain now. So notice E is lowercase, E of t, and then your output is G of t. That's the force I'm putting out. So again, this is error in distance, and the G is a force, right? So I have the error, I multiply it by K sub P, which is my proportional value. The derivative of the error, dE sub t over dt, and then you multiply that against K sub D, that's the derivative term, and then the integral of the error, integral of E of t dt, is then multiplied against K sub I. Right, the integral term. So that's now the objective of this is to tune these three parameters to achieve your objective. Well, what's your objective? What is your objective here? What are we trying to do? What's our goal? Well, one, like I said, we want the system to be stable. I certainly don't want it to blow up, right? If I'm trying to adjust the position of a coin, I don't want it to, blow up, right? I don't want it to diverge, right? So I want it to be stable. I also want to put the coin, I want the controller to put the coin in the spot I want it to put it at, right? But there's more than one solution, because it turns out that depending on how you design the controller, it may make the system stable, and it may put the coin eventually where you want it to be, but it may take a long time. That's the rise time. That's how long it takes to get the coin into position. Alternatively, it may get it there really fast, but it may overshoot, right? It may pass the mark and then have to go back, right? And so there's a rise time and the overshoot time, which is kind of like the performance of the controller. It's how effective it is. There's also control algorithms that are outside the scope of this class, but they allow you to actually apply an objective function. So you can say things like, well, I want to get the coin into position, but I want to use the least amount of energy to do it, because the coin manipulator is running on a battery. I want the battery to last as long as, I don't really care how long it takes to get the coin into position, but I do care how long the battery lasts. And the more force I put on the coin, the faster the battery will run out. So you can actually there's ways to do, there's this thing called a linear quadratic regulator that allows you to automatically tune these parameters for a specific, or you may say, well, I don't care how much force I apply as long as I get the battery there as quick as I can. Get the coin in the position as quick as I can. Or you may have an objective that says, my main thing is I don't want to overshoot. I don't want to pass the mark because that would be really bad, right? So there's different objectives. In other words, there's more than one right answer to this. It depends on what you're trying to achieve with this. Okay, so anyway, so taking this down into the S domain, it's trivial. This just becomes capitalize the G and the E. Notice I actually dropped the E here. And then so this is just G of S equals KP plus SKD, S of course replacing the derivative, and then plus 1 over S KI, or I could have also wrote K to the minus 1 power there, because that's replacing the integral. And then I also went ahead and put it into a better looking form by multiplying this by S over S, so I could get rid of the S to the minus first power term and basically end up with a order 2 polynomial in the numerator, order 1 polynomial in the denominator. Does that make sense? And this is just algebra. Okay, so sometimes you don't need a PID controller. You can get away with a PI controller. That's where you just drop the derivative term. Or sometimes you can get away with just a PD controller. You don't necessarily need all three. The reason I dropped the D is because it turned out that this actually got really complex to work out on slides if you have all three terms. So I just simplified it and made it a PI controller. So because I dropped the derivative term, my SKD term went away, and now I just have KP plus 1 over SKI, or alternatively I could write this as KPS plus Ki over S by, again, just multiplying by S over S. Make sense? Okay, so now we want to calculate the open loop transfer function. So we have our controller, we have our plant. So we have the controller, which is the PI controller. We have the plant, which is the first principles physics model of the coin. And I can calculate the open loop transfer function by taking my PI controller and just multiplying it against the plant. So if the controller is KPS plus Ki over S, multiplying that against the plant, which is the coin, which is 1 over mass divided by S times S plus B over M. And I'm going to just set the mass to 1 and the friction to 1 just so I don't have to deal with those terms. So M is 1 and B is 1 now. So that allows me to simplify this a bit. And then so then I just carry out the multiplication, and I end up with KPS plus Ki over S squared times S plus 1. You guys see that? So I just took, I just took these two guys and multiplied them, and that's my open loop transfer function. And then to get the closed loop transfer function, you just take the open loop transfer function and divide it by 1 plus the open loop transfer function. And that will give me the whole system. Now, of course, that's going to take some effort because that needs to be cleaned up, which I did here. Now, this is a little, this took me some time. So this ends up reducing down to KPS plus Ki over S to the third power plus S to the second power plus KP times S plus Ki, assuming I did my math right here. Okay, and then the idea is I went through and I solved for Kp and Ki. Now that's not necessarily the way, and you guys know this from robotics, you don't necessarily have to solve it that way. But let's just skip over that just for a minute now. Just assume that I chose my two values. In this case, my proportional is 0.3125 and my integral coefficient here is 0.0313. Okay, so I chose those, and so in order to evaluate, I then calculated the step response. Now this is the step response from the simulation. If I had calculated the eigenfunctions, I would have gotten the same, and then just converted the frequency domain to time domain, I would have gotten the same thing. But in this case, I just did a simulation in MATLAB, in Simulink, and you can see that the system is stable, doesn't blow up. And you can see that, well, this shape, it's the impulse response. This isn't really that meaningful, other than to tell us it's stable. I think that's the only thing the impulse is going to be good for. However, if I do the step response, now this is something gives us some insight, because the step response is equivalent to me saying, I want the coin at 0, and now I want to move the coin to 1. Right? So the step response is more of a realistic kind of a usage scenario. And you can see that the blue line is my set point. That's where I want the coin to be. And the yellow line is where the coin actually is. And you can see that, it's kind of bad. In fact, it's embarrassingly bad, because first of all, it took this yellow line a while to get up to that 1, and then it blows right past it, and it wind up at 1.2, and then it comes down very slowly until it converges on 1. So it worked, it's stable, and it gets the coin to the place it needs to be, but I mean, it's kind of embarrassing how badly it controlled it, right? I don't think it's a very good response. So as I mentioned, you can look at these different aspects of this. Like sometimes this is often called the rise time, which is how long it takes the amount of time it takes the controlled variable to reach the set point initially. Now in this case, you can see that is about 7 seconds. You can't see it. I'm sure you guys can't see it in the back, but the horizontal axis is 0, 5, 10. So there's a tick mark. There's a tick mark every 5 seconds. So the coin is literally, it's taking 7 seconds to get up to the set point, and then there's an overshoot by about 1.2, so that would be 1.4, so that would be about 1.25 overshoot. So if I'm trying to move the coin 1 meter, it's overshooting by 0.25 meters. And it's taking 7 seconds just to get to 1 meter, right? Which is, like I said, that's pathetic. So the way you fix that is you can tweak these control variables. The proportional coefficient, I can increase it to 1.25. And that actually has an interesting effect. So this is the before and this is the after. So this is the before is what I just showed you on the previous slide. But when I increase the Kp, it reduces the rise time to about 2.5 seconds from 7. But then it does this thing where it overshoots and then it comes down and undershoots and then goes back over and overshoots and then settles down. So this kind of, I don't know, I mean, I got a better rise time, but I don't know if this behavior is preferable. This is kind of bad too. It's ringing up here. It gets up and it rings. On the other hand, I can increase the Ki, the integral option, to 0.3130, which, strangely, I think this is with the original Kp. I believe this is with the original Kp. So this gives me a better rise time, but a bigger overshoot. So some of this is, one approach, and I think you guys did this in robotics. One approach is to hand tune these values to try to get your desired result. There are some algorithms to automate this, obviously. But as long as you understand, the fact that you can change the shape of this thing by manipulating these variables, that's really the only thing I want to get across. Okay. Also, I thought it would be interesting to plot the force too. So one of the things about that diagram that's a little confusing is that I have the set point in blue and the position in yellow, but you don't actually see the force. You just see the input to the whole system and then the output. What about that intermediate value, that force value, right? That's the value that's actually being output by the controller, right? So I was showing this and I was showing that, but I was skipping this. So what's the input to the plant? Well, I added that with this orange line. And so this is the force that I'm being applied. And it's kind of interesting how, look at that, so when I change the set point from 0 to, I don't know why I changed. Oh, no, that's right. Yeah, sorry, that's the same. I thought I changed the vertical axis, but I didn't. Or maybe I did. Anyway, when I go up to about 0.45 here, you can see the force jumps up really fast, right? But the resulting change in the position is, you see how the position kind of lags behind the force I put, and then the force kind of comes back down, not when I reach the set point, but even before I reach the set point with this yellow line, it compensates by basically pulling the coin back, right? So once this force starts coming down, I'm like, I'm letting up. I don't start pulling it back until the force becomes negative, right? So I kind of push it forward, and then I let up, and then I kind of snap it back at this point, and then I kind of level it out here. Once I reach the coin where it wants to go, obviously the force kind of becomes 0, right? I don't touch it once it gets to where I want it to be. Okay, so and then here's a sinusoidal input. This one's kind of interesting. This is like saying, well, I want to take the coin and I want to go like this. I want to constantly be moving it back and forth. Now, the interesting thing there is that the blue is the set point and the yellow is where the coin is, but look what the yellow is lagging behind, right? So there's like a delay in there. I want the coin to go like this, but the coin's actually lagging behind. And also notice that the yellow line, it kind of overshoots and undershoots the peaks of the input sinusoid. And again, that's stuff that I could clean up by tuning the controller. Okay, so that's all I want to cover in the continuous domain. Now I want to switch over and talk about the discrete domain. You might be surprised by this statement, but it's actually impossible to create an S-domain controller with a computer. It can't be done. Because computers are, they're discrete. They're not continuous systems, right? Processors. In fact, the only way to create a true continuous controller is if you had, for example, a greenhouse where you were controlling the amount of, you were lifting up the top of the greenhouse to let external air come in, but you were doing that based on the expansion of the metal in the roof. Like if you design the roof to, when it gets hotter, it expands and it lifts up, and when it gets colder, it contracts and it comes down, and you controlled the airflow into the greenhouse based on the heat, but not with a computer, not with a processor, but by designing special mechanical shutters that open and close based on their physical properties. That would be a continuous controller, but anything controlled by a processor is going to be discrete. And for that reason, and you might say, wait a second though, I thought you said that you simulated the thing in MATLAB, the S-domain. Yes, but that was an approximation of a continuous system. The way that works is through this thing called the Z-domain. So the idea with discrete time, first of all, what's the difference between continuous and discrete? What's the definition of continuous definition? Yes, do you know?
Continuous, it can be any possible value within the range. usually real numbers or something like that. Discrete, there's a finite set of possible values.
Right. Yeah. So the way I think about it, actually with discrete, it's not necessarily finite. You can have an infinite number of discrete values. The way I think of it is if you pick any two values, in a continuous system, there's an infinite number of values in between those two values. Whereas in a discrete system, if you have two values, there's a finite number of values between two values. Does that make sense? Now, the number of values can still be infinite, and it would still be discrete. But it depends on the number of values in between two values. So in a discrete time system, a signal is not, like a signal like I was showing, like x of t, right? Time, x versus x of t, where t is time. T can be anything, right? It's time. It's a continuous variable. And if I have any two time slots, there's an infinite number of possibilities that I can explore in between those two. Whereas in discrete, you're taking a signal and you're measuring the signal at specific sample times, right? Usually they're uniformly measured. They have uniform intervals where that interval is the sampling period. Guys with me? Okay, so that's discrete. And normally, there's some notational weirdness with that. Usually in a discrete system, if you have a signal in a discrete signal, instead of parentheses, this isn't always the case, by the way. This is just a notation. You'll see different people write this different ways. Usually they use brackets for the sample number. So x of n, where n is the sample number, would be the discrete form. If you have x of t, you would usually use the parentheses. You guys with me? Okay, but anyway, that's just the brackets is usually denotes a discrete. Okay, now what's this z all about? Okay, well if n, so x of n, x of n is a signal, n is a sample number, right? Sample 0, sample 1, sample 2. If n is the most recent, if we consider n to be the most recent sample, then in the z domain, you'd have x, capital X, you'd still capitalize the x, because the z domain is like the discrete form of the s domain, right? You have x of z would represent the current sample, the current value, right? But then if you take z to the minus first power and multiply it against z of x of z, that represents the previous sample, which would be like saying x of n minus 1 in the time domain. You guys with me? Again, assuming n is the current sample, the current time, or the most recent sample, I should say, the most recently sampled value is n, right? X of n. Whereas z minus 1 times x of z is the previous sample. Likewise, if you had z, say minus 7, z to the minus 7, times x of z, that's the sample that was collected 7 samples ago. Okay, now that's what is up with that? It's kind of arbitrary, right? So this is just a picture of. Sorry, I don't know if how this looks in the back, but so this is just a graphical representation of a continuous signal that might look like this. And I don't know if you can see it, but there's like a curve that goes like this. It's kind of washed out. And so there's like a gray line that shows a curve. And then you've got this red line, which is the discrete form. And the dotted lines are the sample points. So you can see that there's samples that are spaced out, uniform widths, uniform spaces. And at each space, wherever the continuous line intersects one of these sample points, like whenever this gray line hits one of these dotted lines, that's your sample point. So then if you connect together all those sample points, it looks like this weird, pixelated, digitized signal, right? And the idea is that the red line is meeting the gray line at each sample point, but in between I have no information. And because I have no information, you end up having to just essentially instantaneously change the discrete signal to match the continuous one at each at each sample point, right? So anyway, that's, sorry, I should have had that one slide earlier. Okay, so as I mentioned, the Z domain and the Z transform is a way to take a time domain, or is a way to conceptualize a transfer function in the discrete domain, right? For discrete signals. Okay, so one of the questions is that, well, how does this apply? What does this mean for stability? I mean, are the rules the same? Like, what was the rule for S domain? If you have an S domain transfer function and you calculate the poles, if the poles are in the left-hand, what's it called? Left plane. Left-hand plane, sorry. Left-hand plane, meaning that the poles are on the left side of the plot to the left of the zero axis, right? Then it's stable. But it turns out that that's not the same for the Z domain. In fact, the Z domain stability criteria is a little bit wishy-washy. A system with poles close to Z equals 0, meaning the origin, right, will settle rapidly. What do I mean by settle rapidly? It'll converge rapidly. A system with poles that are close to the unit circle, so unit circle. Now remember, Z is a complex number. So if you draw a unit circle around the origin, any poles that are close to the unit circle will settle slowly, but it'll still be stable. A system with poles right on the unit circle may have a sustained response, or with certain bounded inputs may have an ever-growing response. So in other words, if your poles are on the unit circle, then it may or may not be stable. We don't know. But if you have poles outside the unit circle, then it's definitely unstable, right? So those rules are kind of not quite as definitive as they are in the S domain. Okay, so let's look at some examples here. So in a continuous system, this was an example I had earlier in the lecture here. I had u of t equals y of t plus the derivative of y minus 6 times the integral of y. And then the S domain transformation was really simple. Just, add your s's in there appropriately to replace the derivative and integral. Derivative is s, integral is 1 over s. Now, in the discrete version of this, I forgot to replace these parentheses with brackets, sorry. These should be brackets, but it's u. Now notice I changed t to k, right? So I still have u and y, but now t is k over here on the discrete side, right? So instead of using t, I used k, yk. K is the sample number. And so I have y of k plus y of k minus y of k minus 1. Well, what is going on here? What is this all about? Well, this is basically saying the current sample minus the previous sample. What is that? Well, that's the derivative. The derivative is the current value minus the previous value. That's the derivative. That's how much I changed in one sample, right? Likewise, the integral is now a summation, right? But this kind of, I have to sum from the beginning of the signal, I equals 0 to k. I have to sum up all the samples to create the integral, right? Makes sense, right? Okay, so this just, okay. So it turns out, though, that in the Z domain, I would replace this derivative. And by the way, this is called a difference equation as opposed to this is a differential equation. In the discrete space, it's called a difference equation. And the reason why, you can see right here, I replace the derivative with a difference, right? So that's why they call this a difference equation. But anyway, I replace that derivative with z minus 1 over z, right? As compared to the S domain, it was just an S. So why is this more complicated? Why can't it just be z? Why does it have to be z minus 1 over z? Likewise, the integral is z over z minus 1. Why does it have to be, it seems unnecessarily complicated. Why what is up with that? Well, the reason is it's actually. Let me skip. I'm going to skip ahead here a little bit. So there's an interesting reason for that. So first of all, I mentioned that the first difference, or the first derivative, right? First derivative is z minus 1 over z, right? As again, remember S was just S. Laplace was just S. Why is it z minus 1 over z? Well, the reason for that is because if you divide this, if you divide the numerator by the denominator, you actually get 1 minus z minus 1, right? These are equivalent. And remember, I mentioned earlier that z minus 1 has a special meaning. It means the previous sample, right? And 1 means the current sample, right? I mean, of course, I'm assuming that I'm multiplying by the z-domain variable. 1 is like saying the current sample, and z minus 1 is the previous sample. So this is literally just saying the current sample minus the previous sample, right? And that's the derivative, right? That's the difference. That's the rate of change of the signal in the discrete space, right? It makes sense, right? The integral one, though, is a little different, though. The integral one is, anytime you have an integral, it's z over z minus 1. This is the one that's kind of wild, because if you do the same kind of division here, like so if I take z minus 1 and divide it into z, okay, the answer is 1, but has a remainder, like the answer is 1, and I subtract the divisor out, right? 1 times the divisor. So I subtract z minus 1. I'm just doing polynomial long division, right? I subtract that out and I get positive 1, right? Because I get a minus here and a minus there, and becomes a positive. It's 1, right? So it's 1 with a remainder of 1 over z minus 1, right? Right, so it's just 1 plus z minus 1, right? Okay, now the problem though is that, can I keep going with this? Can I repeat this? Well, if I take z minus 1 now and I divide that by 1, okay, so I'm going to multiply the divisor now by z to the minus first power, right? And that ends up giving me z minus 1 times z minus 1, z to the minus 1 power times z minus 1 is, z to the negative first times z is just 1, right? Minus z to the minus first power gives me a remainder of z to the minus 1 over z minus 1. So I get this. Make sense? Okay, so what ends up happening here is I can keep doing this over and over again. Okay? And so basically what I end up with is, as I keep expanding this, so in other words, I did the initial divide, I got this. I calculated this remainder, and I got this. And then I calculated this remainder, and I got this. So what I end up with is 1 plus z minus 1 plus z minus 2 plus, and then it keeps going and going forever. So basically what this ends up becoming is, it's like saying, well, the integral is the current sample plus the previous sample plus the previous sample plus the previous sample plus the previous sample all the way back in time to the beginning, right? Which is the same thing I showed in the time domain here. It's just a summation, right? It's adding up all of the previous samples, right? That's the integral, right? But that was in the time domain. In the z domain, it's just z over z minus 1. Make sense? So this summation can be replaced in the z domain as z over z minus 1. But if you try to divide it out, you end up with an infinite repeating pattern of 1 plus z minus 1 plus z minus 2 plus z minus 3 and so on. Make sense? Okay, so that's basically the difference in the integral in the z domain. Okay, so and I'm running out of time here, so I'm going to skip ahead real quick here too. Okay, so now the real problem here though is, the problem we have to solve is, if you have a plant and the plant has dynamics in the S domain, right? How do I convert it to the Z domain? How do I make a continuous system discrete? The way you do it is through, there's several ways to do it actually, but the best way I found is this thing called the Tustin transform. The Tustin transform it's actually a really simple concept. You just take, I don't know how they figured this out, because this is crazy, but applying it is simple. You just take the S, if you have an S domain transfer function, and you replace that with 2 over the sample period, T sub S. That's the time between samples. Likewise, 1 over T sub S is your sampling frequency. And you multiply that by Z minus 1 over Z plus 1. So that'll go from S domain to Z domain. Now you might say, why would we have to do that? You have to do that anytime you design a processor-based controller for anything. You have to do this, because you cannot implement S domain directly on a processor, right? Because processors have sample periods, which is why we've, so far in this class, I've emphasized the pulse width modulation and the periodic nature of controllers. Well, that all represented the the notion of a sample period. Okay. However, you have to also keep in mind that this is just still an approximation. It doesn't really work, because if let's take a really simple S domain, 1 over S, S domain transfer function, 1 over S. What is 1 over S? Well, it's an integral, right? It's an integral. It looks like this. If I have, it's an integral. If I hit an integral with a step function, a step response. So I go from 0 to 1 and I keep it at 1. Well, an integral is just going to be accumulation, right? I'm going to give 1 to an integral, and it's just going to look like that. It's going to look like a ramp, right? In the continuous space. However, in the discrete space, if I take my Tustin transform and I stick it into this simple 1 over S transfer function, I get this. And then I plot that, in this case with t equals 1 second per sample. Obviously that's slow for a modern processor, but just, you could scale that down. What you end up with is this, check this out. You got this orange line. And basically what ends up happening is the Tustin transform gives you a digitized version of the integral, which looks like a stairs going up, right? Sampled every 1 second. If you look at the horizontal axis, it's 0 seconds to 10 seconds. Okay? But here's the cool thing about the Tustin transform. It's a little nicer than some other types, because notice what happens at the beginning here. At time 1 second, the Tustin transform gives me 1/2. And you might say, well, what's significant about that? Well, because if you look, if I was just doing a really simple, like looking at the value of the continuous and just hitting that would have been 0. But notice the Tustin is 1/2, because it's actually the average value. It's giving me the average value between time 1 and time 2. At time 1, the continuous is 0. At time 2, the continuous is 1. The Tustin's giving me 0.5 throughout that interval. So the Tustin is actually pretty nice in that it gives you the average value, and if you look at the way it intersects the continuous value, it's actually intersecting at the halfway point. So it's intersecting at 1.5, 2.5, 3.5, 4.5, right? So it's actually a little bit nicer than just doing that simple thing I showed you on that previous slide. Yeah, it's actually nicer than this version, because I don't know if this version, notice how it just meets the continuous at whatever the continuous value intersects each time period, right? So it's nicer than this one. This is not the Tustin transform. This one's using a, I forget, there's several different, I can't remember the other ways to do it. But Tustin is the nicest one. That's the one I prefer in terms of going from S to continuous to discrete. And so that's really all there is to it. And then there's I'll finish this lecture next time, but basically I take you through a PID controller, or actually PI controller, using the Z domain. And I'll finish that next time. But I think you guys have everything you need for the quiz. Any questions? Am I out of time, or 20:35? Oh, I got a few minutes. Yeah, sorry. I actually got 5 minutes. Keep making that mistake. Any questions so far, though? You guys with me? Okay, so let's see if I can get through that example here. So, okay, so here's my here's the Tustin transform here. This is just the reference. That's the Tustin transform. And my physical model for my coin example was 1 over ms squared plus bs, right? So I want to convert this to discrete. So I convert this to Z domain, I just substitute S, right? And I get, and actually, sorry, this was when I set the mass to 1 and the coefficient of friction to 1, so it's 1 over S squared plus S. When I do that, I get, well, I get something that looks kind of ugly at first, because S squared is the Tustin value squared plus the Tustin value not squared. So I have to work this out to make it look a little nicer. Also, I have to choose a TS value for this. I got to choose a time step. I'm going to use 1 second just to make this as simple as possible. So I go through and let's see, the first thing I do here is I square this term, which gives me this, right? I square the numerator, square the denominator, and square the 2. That becomes 4. And then I create a common denominator here, which is not too hard. I just have to take this and multiply it by z plus 1, this side, right? Which gives me a common denominator, z plus 1 times z plus 1. And so that's my numerator. And then I can take the denominator here and just flip it up to the numerator, right? Okay, so I end up with this. Now, by the way, yeah, I got this in the right form, right? Y over U, yeah. Y is the position, U is the force, input force. Okay, so I've got that, and then let's see, I multiplied out these two terms. So z minus 1 times z plus 1 is z squared minus 1. And then I multiply out take the 4 and distribute it over there. And then I just add up everything, and I end up with z squared plus 2z plus 1 over 6z squared minus 8z plus 2. That's my z domain transfer function for the coin model, right? And then I wanted to get rid of this 6, this leading 6. I wanted my denominator, I wanted the polynomial in the denominator to have a leading coefficient of 1. So I just divided everything here everything by 6. And then I took the denominator and I converted it into z minus 1 times z minus 1/3 because I wanted to get the roots, the poles, right? I need the poles. And of course the poles end up being 1 and 1/3. And so what does that mean for stability? Well, I mean, I don't know. It's unclear because that 1 is on the unit circle, right? Remember, it was kind of wishy-washy with regards to what happens with poles on the unit circle in the Z domain. So, but I mean, we know that we knew it was unstable in the S domain, right? So we can expect it to be unstable in the Z domain, even though one of the poles is on the unit circle and one of them is inside the unit circle. Okay, and so now this is the part that I think is really fun, because you look at this, you say, all right, I got in the Z domain, now what? Well, the whole reason we did this is so we could implement this on a processor, right? We want to put this in code, right? We want to run this on a program, right? So, so we got to get it, we can do it algebraically. We can take that Z domain transfer function and we can, again, transform it algebraically into a form where we're calculating y of k, the current sample of y, as a function of samples of u. You guys with me? But here's the thing about it. You have to make sure that when you do that, on the right-hand side of the equation, all of your z exponents have to be negative. The reason is you're not allowed to have positive z coefficients because that would imply that you're looking into the future, right? Remember, the negative z coefficients means the past samples, right? So that's the trick. So, okay, so hold on, sorry, skip. So basically what I end up doing here is I just multiply this by z to the negative second over z to the negative second. I do this only to make all the z exponents less than or equal to 0, right? You guys with me? Because the 0 exponent's fine, that's the current sample. I can't have positive exponents. So this gets rid of all the positive exponents, right? Then then the objective is to get y of z on the left-hand side, and on the right-hand side, I can have a mixture of y of z's, as long as they have negative z coefficients, right? And u of z's. Why? Because that allows me to calculate the position of the coin based on the previous position of the coin as well as previous forces. You guys with me? Does it make sense? Now ideally, I don't want to go back to the beginning of time though. I only want to have enough samples in the past. I want to have the minimal number of samples in the past, right? You guys with me? I don't want that summation and go back to the beginning of time. But it turns out that you can do that because in this case, see, I did do the brackets this time, sorry. Y of t is 1/6 u of t plus 1/3 u of t minus 1. 1/6 u of t minus 2, right? So far, those are u's, right? So I'm basically saying the position is based on previous force values, right? But check this out. You also can have y's in there. The previous y and 2 samples of y ago. Now you might say, why is that? Because think about it. I can evaluate this model based on my current force, my previous forces, and a few previous positions. But I don't have to go back to the beginning of time. I only have to go back 2 samples, right? So all the state information I need to figure out where the coin is simply based on no more than 2 samples ago of y and u. You guys with me? Does that make sense? I think that's cool because you don't, like I said, it's not like you're accumulating since the beginning of time. You only have to know the recent history to figure out where the coin is. You don't have to go all the, now again though, that depends on, it depends on the function, right? But in this function, I didn't have to go that far back in time. And of course it depends on the order of those polynomials. You guys with me? I think that's, I don't know, I was always impressed by it. But okay, so I think now I'm out of time. So we'll see you we'll see you in lab this week, and don't forget about the quiz.